Good evening, everyone. Welcome here in University of Lincoln. I'm Professor Andrzej Zwolentowski. I'm head of School of Mathematics and Physics. I'm just here to welcome you. Few sentences of housekeeping. In case of fire, fire exits behind me and also on the left and right hand side above you. This is all for housekeeping. Those who attend our lectures from previous years might notice that you book ticket. We announced a little bit longer time because some member of the audience wanted a bit more questions to the audience. So we booked like for 7:20. It might finish earlier, but if you will have more questions, there is time for that. In case you want to exit the room, don't be shy. Kind of just go if you need to exit room for any reasons. Before we give floor to our speaker today, just as introduction, and by the way, on your desks you might find leaflets with dates of all our future public lectures. If you would kind just distribute them among themselves, you can take home and book yourself for any future lectures might you would like to come again here. Our school is very new school. We're just 3 years old. We started our public lectures here, and as you notice from names on the list of public lectures, they all named after a particular individual. Very obvious names for Lincoln, of course, Isaac Newton, this building named after him, this lecture hall named after him. Another very obvious name is George Boole. However, as our school develops, we discover that there are more people associated with Lincoln and Lincolnshire, as it is known in principle for scientists. Scientists know that there are more of us than just Newton. Although kind of very often then time goes by, centuries pass, and people think that Newton and Einstein did everything. There were a little bit more of us, and not all of scientists kind of survived in memory. Example is Edmund Weaver. So today we start new type of annual lectures named after Edmund Weaver, and this lecture is the first annual lecture in astronomy. So who was this Edmund Weaver? Edmund Weaver lived in the times of Isaac Newton. He was younger than Isaac Newton. However, they overlapped. He was from a small village, or maybe it was town at that time, a village, Freeston, in between of Graham and Lincoln, as you see on this map. This is very tiny village. It's actually formally now incorporated in a nearby, somewhat larger village where his grave is. And what do we know about of his years of life? Basically, not much more than written on this gravestone. And it looks like his family probably who erected this gravestone, they kind of thought that he will be forgotten. So they wrote all his biography almost there, like a job application CV they call nowadays. And it does say there that he was one of kind of very remarkable people in astronomy in his time. We do know that contrary to Isaac Newton, he did not study in university. He probably did not have simply enough money. He was completely self-taught. He worked as his main job was land surveyor. He had some kind of revolutionary ideas in land surveying as well, because we found there are records that 70 years after him, people who do land survey are telling that we should incorporate these ideas in Britain, which were proposed by this gentleman. But we are here for astronomy. As I said, he was forgotten to the degree that in 1900, in the journal Observatory, Greenwich and Cambridge astronomer Lynn was writing a correspondence letter where, among other lines, he was asking, is anything known of his uncommon genius? Because he was struggling to find information, so already in 1900 was difficult. Almost everything we know about Edmund Weaver was thanks to his powerful friend. And that gentleman had his portrait, of course, made because he was a fellow of Royal Society, William Stockery. He was physician, clergyman, and antiquarian. And through his friendship and acquaintance with Edmund Weaver, he became very much into the astronomy, astrology, so he became very big enthusiast. And as a powerful gentleman, I actually deleted some letters after his name. He was not only fellow of Royal Society, he was fellow of quite a few societies, as you might imagine from his costume. And he was very good. So these sentences, uncommon genius, are his words. So what so special Edmund Weaver actually did? As part of his basically hobby, he was publishing a magazine called The British Telescope. Not many copies survived. In fact, Mr. Lynn was able in his time find only one copy in University of Cambridge in 1900. Later people found a few more, and in 2010 or 9, I believe, they reprinted a few copies, and this kind of images there, they show this. Lynn puts that Weaver, however, seems to deserve great credit for his tables. So what he published there were astronomical tables. And that was quite tedious type of work for particularly those of you who astronomy lovers. In the times with very still simple telescope and no computers and no calculators. His tables were used by other people who managed to reasonably well describe transit of Venus, which happened in lifetime of Edmund Weaver, but more importantly, they managed to correct dates of ancient eclipses reported in Plinius the Elder, so in the time of Pompeii, and they kind of make calculations that it seems tables of Weaver can make nice correlation with dates of Olympiads, which were used in those years to mark when things happened. Tables did not not all of them kind of survive, only very small things. He was also a supporter of heliocentric system, and you heard some of your previous lecture, which was still topic of dispute in time, and in fact Newton was also one involved, and some other bits. Today, we just kind of sort of celebrate his kind of memory, but we won't talk about his discoveries. We are very happy that we start in our school new direction in astrophysics and astronomy in September, and we've been very fortunate to have Dr. Phil Sutton join in our university from University of Loughborough in a particular nice time of September, because September, world seen one of largest missions ever made by our basically civilization, Cassini mission, ending its time with Saturn, and Dr. Sutton is an expert in Saturn. So how nice this coincidence. Without further ado, I give floor to Phil, and please enjoy your lecture and prepare questions at the end as we have time for that. Thank you.
So, today I was going to talk basically about Saturn and Cassini. I spent quite a number of years looking at a lot of these pictures that I'm going to show you. We've only got a short amount of time, really. but I'm going to show you some of the things that I think are some of the more exciting discoveries that we found by basically putting a spacecraft around this fantastic planet, really. There's a lot more to it than that, but this is some of the more exciting things, I think, that some of it you may have seen, some of it you may not. So I'm hoping it's going to be an interesting talk for you. So for those unfamiliar with Saturn, it's the sixth planet out from the Sun. It's located just beyond Jupiter. It is actually the second largest planet in our solar system. It's the only one that's got significant rings. All of the other outer planets do have rings, but they're not as significant. So Saturn's ring has got the biggest ones, and they're the ones we're going to be actually looking at hopefully today, as well as some other things. The actual rings themselves are predominantly made from water ice. And you can see from here that the temperature is incredibly low. So the further you get away from the sun, the temperatures get quite low. And yeah, they're basically it's just ice, those rings are predominantly. This is the Cassini-Huygens spacecraft before it was launched. It was actually Cassini-Huygens, it wasn't just Cassini. And it was actually in two parts. So the main Cassini, the actual orbiter which went around Saturn, is actually the main part there. The Cassini-Huygens spacecraft in its entirety was named after the actual astronomers that first found certain elements around Saturn. So the moons, and actually, well, probably Titan. So that's why the Titan probe was named Huygens. And that actually went down into Titan. We've got some images as it went through the atmosphere and what you can see there. But that just gives you an idea of the sort of scale that it was. So it wasn't necessarily a small spacecraft, it was a fairly sizable one. And we sent it quite a long way in the solar system. There isn't many other spacecraft that we've launched that have got as far as that. There's only a few more that have gone a bit further, really. So that is actually the trajectory that it took. So you can't just launch a spacecraft and it goes straight to the planet. You actually need to kind of do a lot more maneuvers than that to either give it more velocity or, these planets are actually moving themselves, so they're all orbiting as well. So you've got to kind of do a bit of a curved trajectory. And Cassini actually needed to do two inner passes to Venus to actually get enough velocity to reach further parts of the solar system. And it actually peaked in velocity on its second pass to Venus. That was about 45 kilometers per second. So it's fairly fast. Still took 7 years to get to Saturn, though. It's quite a long way. You're talking billions of kilometers sort of distance-wise. So even at kilometers per second, it's still a long time to get there. When it actually got to Saturn, you're still doing orbital speeds around that same sort of magnitude, probably around about 20 to 30 kilometers per second when it was actually in orbit. So it's fairly fast. And you may have heard, actually, during the last week the last year, because it started in April, actually, when it started to do those close passes to Saturn before its final crash through the atmosphere, it got very close to the rings. And if you're doing speeds of 20, 30 kilometers per second, you have a collision with any material that can be quite catastrophic, which is why they left those sort of maneuvers till the very last part of the mission. So I'm going to start with something that's not unusual at all. We have quite a large hexagon shape on Saturn. It was actually first discovered kind of in the 1980s when the Voyager probes went past. So they're kind of our most distant spacecraft at the moment. And when Cassini got there, it's still there. And it's a very large, perfect hexagon structure. 20,000 kilometers, that's quite large. It's been there for decades. If you go and kind of search this on Google, it'll be a bit mixed what you'll find. You might find some conspiracy theories about aliens, because apparently what they will do is they'll go to Saturn and build a large structure like that. I don't know why, but that's what Google tells you. I can understand why people might think things like that. It doesn't look natural. It's in the cloud structures. It's not a physical structure on Saturn, and it stays stable like that. While Cassini was there, they actually found that it was changing colour as well. So over the 4 years, we've got these images here, you can see it's quite markedly changed colour. Now, what they think has happened there, it's possibly seasonal. So what you have to bear in mind is that because Saturn is a lot further out from the Sun, it takes a lot longer to do a single orbit. So you're looking about nearly 30 years to go around the sun once. And while it's doing that, it's exactly the same as Earth. It has an inclined rotation axis, so the sun's shining on the polar, on the hexagon structure for a long period of time. And I think there's some kind of additional mixing going off there, some chemical reactions which might change the colour. But I have got a video here that you can watch. So there was a lot of, it was a very strange structure to find there. And, there was talk of it not being natural. If it's natural, how can it occur? And some people did some laboratory experiments with a rotating fluid. And they managed to actually produce this hexagon structure in their experiments. It's not exactly the same. So with Saturn, it's more of a three-dimensional thing that's happening there. You're getting a lot more mixing vertically through the actual cloud structure, and there's some possibly additional physics going off as well. But the purpose of this is to show that actually you can create those sorts of structures naturally at a lot smaller scale. But you can see that the straight edges you've basically got like vortexes on each edge, and they actually maintain the straight edges, and it keeps it fairly stable. It's all basically down to like, you can compare it to like a jet stream that we have on the Earth. It's kind of almost comparable latitude. I think it's probably a bit higher. You have these very fast winds in that part of the atmosphere. And with the right parameters, you can replicate that sort of thing. So, unfortunately, it's not aliens. It's not as exciting as that. It's just something we don't understand. And one thing that, with astronomy and astrophysics, the more we actually go out there and have a look at things, we're finding a lot of things like this we don't initially understand. And one of them, I'll show later on, is that you've got these rings of Saturn, and then when you look really carefully, there's actually moons inside them. There shouldn't be moons inside them. They can't form where they are, yet they're there. So that's another puzzle. We actually haven't found that one out yet. But the more we're looking at things, the more we don't understand, the more we've got to try and understand them. So another thing that happened when Cassini got there was these storms that were occurring. So you've got these massive storms, and you can see on the top there that there's a large storm happened there, and basically as Cassini was orbiting and watching, it actually went around Saturn, and actually it met up with its tail again. So it actually went all the way around and met up with its own tail. And these storms happen fairly regularly, but they don't happen in both hemispheres at the same time. So again, it's potentially seasonal, but this time round, you've actually got the rings. So, we're not familiar, with Earth. We have seasons, we understand them fairly well. But when you've then got very large rings around the planet, it casts these shadows on the planet, which is going to alter how the seasons are. So as the planet's tilted, you get more shadows. There'll be a lot less sun reaching the southern hemisphere, then a lot more sun on the northern hemisphere. So you have quite a large temperature difference there, which is most likely going to drive these storms. And as you can see, actually, the rotation axis is tilted a lot more than Earth, so it can be a bit more extreme. Again, I think it's more of we think it's related to this, that's what they tie into. But we actually, although we've been there 10 years, we need a lot more data. We need to send more spacecraft, I think. Now, Titan is actually the largest moon around Saturn. It's actually one of the ones with the most significant atmosphere in the solar system. So it has quite a large atmosphere around it. As you can see, it's quite large in comparison to our moon. It's bigger than our moon. I think there's only one moon larger in the solar system, that's Ganymede, which is around Jupiter. So we can see Titan from Earth. You should be able to see it with actually a medium-sized telescope. You should be able to see Titan. But it wasn't until we sent Cassini and did some very close near passes that you start to find actually that it's quite similar to Earth in the sense of it's got lakes, it's got seas, you've got a lot of stuff like that. The difference is it's not water there, it's actually methane. Because the temperatures are a lot lower. You've got some very low temperature there, so it's at minus 180 degrees, so it's quite low temperature, but you still have liquid and you still have the same erosion processes happening. And that becomes evident when you actually put the probe onto the surface. So today, this is the furthest away we've actually successfully landed a probe, which is quite exciting, really. It was, it's about 1.2 billion kilometers away. it's a long way to send something on its own, land, go through the atmosphere, take pictures and send them back. So I find that quite exciting. But you find that actually, so on the right-hand side is, I think, of a riverbed on Earth, and on the left-hand side, on the bottom, is actually an image taken on Titan by the probe. And you can see the rocks are fairly similar, they've undergone fairly similar erosion processes. So, it might be methane happening there, but it's actually the same sort of erosion processes. And the top image is actually as it went through the atmosphere itself. So there's a few images as it's descending down. And you can see it's got mountains almost the same as Earth, really. And to see those things on another body so far away is quite interesting, really. And yeah. The closest approach that it did was earlier on this year. So during its last manoeuvres, it started to do very close passes to quite a few of the bodies. So a lot of the moons it went very close to, a lot of the rings it went very close to. And on its closest approach, it did a very detailed map of Titan. So you can see a lot of the seas and lakes there, the methane, but also you've actually got the topography as well. So you can see it's actually not even. You've got quite a lot of differences there. So you've got hills, mountains, so it's not a completely smooth surface. And again, they're probably going to be eroded by a lot of this methane rain that we think is there. I'm not sure whether Titan itself is going to be the best place to look for life. There might be other better places. But if we want any methane, let's go there. And this is where it starts to get a little bit more weird. So Enceladus is a moon, it's closer to Saturn than Titan. So Titan's quite away compared to some of the smaller moons. And we didn't really know anything about this until we sent Cassini. And we first saw the ring. So there's a couple of Cassini pictures here where you've got this kind of quite diffuse ring. It's not very even. It's quite an unusual looking ring. And it shouldn't be the shape that it is. So they were looking for a reason why it got there. And what actually they found when they got close to Enceladus was that they had these ice plumes coming out of it. So the actual moon itself was kind of throwing material out into space, and that material was then creating a ring around Saturn. And they did computer simulations simulating that, and they pretty much match what they saw. So they're fairly confident that was what was creating this ring. But that's not the most exciting thing. So if that's sending ice out into space, what's kind of the internal structure like? What's the actual moon like? So they know that because we're getting this ice come out, there's going to be like a water ocean there as well. So there's basically, internally, there's a lot of heat there that's keeping an ocean kind of fairly warm. So I think at the bottom of the ocean, they suspect it's around about 90 degrees or something. You can compare it comparable to like our some of our seas. We have deep sea vents, and you have a lot of life around them as well. So there's no light there. The life isn't using the light to get its energy from. It's using the energy actually from the thermal vents. And Enceladus is going to have exactly the same. It's got quite a significant water ocean. So as a place to look for life, Enceladus is probably one of the best places in the solar system to look. And I don't know what that life would look like, but I suspect it's going to be one of a significant mission going forward to actually send something back out there. Like we sent to Titan, let's send something there. I think the only other one that might be of interest is Europa. So Europa is a fairly similar moon around Jupiter. It's like it's got a frozen surface, and then it's got a water ocean as well. So those two are going to be the best places to look for life. Europa you can actually see with a telescope. So that's one of the Galilean moons. So again, you could look for a small telescope and actually find somewhere that's actually got life. We just need to go and find it. That's what we need to do. So just like the Earth and all the other planets, it's actually rotating, and it's got a rotation axis that it rotates about. Now think about the fact that the actual moon itself is throwing all this material out into space. It's got a frozen surface, but the frozen surface is going to move around similar to our tectonic plates as well. And they found, by looking at the topography of Enceladus that actually there was a fossilized equator that wasn't where its rotation axis is now. So what that's telling you is actually that it's shifted over time. And it's because you've effectively lost some material, that you've shifted the kind of the mass around on the actual moon itself. It's actually shifted the rotation axis. It happens quite a bit with other planets and other moons. We've done it to our own planet. So by warming up the planet and melting the polar ice caps, you're changing the weight, the mass distribution on the planet, and therefore you can actually move the rotation axis. It's measurable. It's not a lot, but we've measured that with Earth. So it happens quite a lot. And again, with Mars, we've done exactly the same sort of thing. You can look at features actually on the surface and show that actually the equator now is not where it used to be. When something's rotating, they're not going to be a perfect sphere. So they're going to kind of bulge a little bit around the equator, which is what gives you the idea that there's a fossilized one there. You just look for these particular features. But yeah, it's just interesting that we've actually managed to do it ourselves. We've actually changed the way our planet moves. Not a lot. So now, the main rings you'll have seen are the bright ones in the actual, or closer to Saturn there. So they extend about 140,000 kilometers from the center of Saturn. And they're about 70,000 kilometers wide. But they're actually a very small part of what's actually orbiting around Saturn. You can actually see it's not very bright, it's quite diffuse, but there's these outer rings. You've got the E ring and the G ring. So the E ring is the one that we saw with Enceladus a while back. And that creates this kind of ring material. That's basically all the water ice, or the inside of the ring, the moon that's then come back out and is now orbiting around Saturn. But there's another one, which is further in. So that's the G ring, which is the one on the right-hand side. I've put a bit of a zoom in on that. That one's even stranger because there's no moon there. There's a very narrow ring of diffused material. But on that edge that I've got there, it's actually like a very bright arc. So it's not a moon, it's an arc of material. And there's no reason for it to be like that. The only reason they can find is that there's an orbital resonance with another moon that's nearby. So there's a moon Mimas, which is actually the Cassini division, which is actually in the main rings. You can see the dark region there. There's a 2-to-1 orbital ratio with that moon, which means that it pulls material out of that. It gets a gravitational tug every 2 orbits, which pulls material out, and it creates a gap. And they think something similar is happening with this arc, in the sense that it's actually forcing it to herd together. So you've got this ring material, and it's gravitationally herding it into this certain area. So a lot of these moons actually act as shepherds. They force the ring material in certain locations, and when you first look at them, you can't see the connection. It's only when you start doing some modelling and you actually look on a computer, you can find out what's happening there. Now, why can you actually see those outer rings? Because when you look at them normally, you look at a telescope from Earth, or when the sun is kind of... So if the sun is shining onto the rings and reflecting back, which is backscattered, you'd see on the right-hand side here. And that would be your main rings only. That's the dense rings. And those rings are made of quite large material. So you're talking around about 1 meter to a few tens of meters in size. And they will then reflect the light back. The very diffuse rings, the ones that aren't very thick, if you've got the sun directly behind them, they would forward scatter the light more. And that's why you can see them showing up on the left up there. So when the sun is directly behind, you start to see these very faint rings. And that particular effect, so the forward and back scattering you get on those particles, helps you to basically decide on the sizes. So we know that by that particular effect, what the particle sizes are. So the outer rings are typically micron size, very small particles, whereas the larger ones, so the main rings are actually meter size and a little bit smaller. There's a lot more mass there keeping together. Interestingly, though, that's not just the only difference. If you've got very, very small particles, you can manipulate the way they move with different forces. So the main rings, you can basically, they're going to evolve with gravity alone, basically. They'll just orbit due to the gravitational forces. The very small particles, you've got like the solar wind and you've got the magnetic field of Saturn, and they can actually manipulate the way they move. So they're very difficult to kind of predict where they're going to be and how they actually evolve, which is why they're a bit more diffusible, because they diffuse the trajectories. So this is what I mentioned at the very beginning about actually having moons inside the rings. And you can see they're not smooth, they're not just a ring. When you look carefully, you've kind of got these little moons inside the ring, which actually then create a gap. And basically at the very edge of the ring, so at the very top of that ring there, you've got something what's known as like the Roche limit. Now, if you're closer to Saturn or any planet than that particular limit, or that distance, if it's a moon or a satellite, it gets pulled apart. So the tides of the planet pull it apart. It can't hold itself together. So it can't form where it is. So the only way, well, we don't actually know why they're there. They could be a lot denser than we think they are, but they definitely can't form when they are from the water ice because of this Roche limit. But anyway, you have these moons in there that are then creating quite interesting shapes. Now, the moons don't move in an orbit in a perfect circle. They move up and down a little bit, they move back and forth, and they then create these waves actually in the ring itself. So you can see you've got kind of vertical waves coming up. You can see the shadows falling on the rings themselves. And the reason why there's asymmetry there, so you've got waves on one side above it and they're kind of below on the other side, it's because the ring material orbits at different speed. So the closer to Saturn you are, it orbits faster, and the further out it is, it orbits slower. So it basically means you get that asymmetry in the waves on the opposite sides. And this will probably give you a better idea of what's actually happening. So that's like a computer simulation that shows these waves forming. So the actual moon itself, it's actually inclined, so it basically means it goes above the ring and below every orbit. And the gravity of that moon, it's significant enough to actually pull the actual ring material down with it and back up, and you get these waves forming. The interesting thing is, well, we kind of know the size and mass of that moon, and it's by looking at what it does to the ring that we know that. So we can work out the mass of it by the gravitational effect it has on the ring. So the amplitudes of those waves and how it evolved can tell us effectively the mass. And this was, again, one of the closest approaches it made to the ring. And it's the same moon, and you can see some of the waves it's creating there. You can't really see on the TV screens, but there's a very thin string of material from the moon going into the actual ring itself. So there's a lot of finer details there. Can you also see that actually there's a lot of lines in the rings as well? I've probably not mentioned anything about them. They're all caused by the moons. So I think there's about 60 or so named moons around Saturn. There's a lot more than that. But basically all of those moons are close enough to have an effect on the actual ring itself, and they create kind of orbital resonances. So they're basically, in certain locations, the ring material will bunch up, and in other locations you get gaps forming. And that's why you're seeing that kind of, all those lines there. And you get some things called like spiral density waves and that, again caused by the moons interacting with the ring. Those things are actually very important for things like planet formation, because planets form in a disk. I say similar to Saturn's rings, those disks have gas, Saturn's rings doesn't. But basically you can use it as a scaled down version of how planets might form. So these spiral density waves we get forming in the rings are exactly how we think the planets form and how they migrate in and out of the actual disk itself. Because if you've ever looked, if you look at exoplanets where they're located, you find a lot of very large planets located very close to their stars. Now what that means is that they didn't form there, there's not enough mass, so they must migrate. So by finding out how these moons interact with the ring and how they migrate, and helping us understand how the planets that we find already located where they are may have got there. Another thing, so this is like an artist's impression if you're on a spacecraft going across the rings. And you've got some nice vertical structures there that look like mountains. So these were right at the edge of the ring. And bearing in mind that the actual rings themselves are only it's almost like a monolayer of particles. So in the very thick part of the rings, it's approximately meter sort of size, and the particles themselves are around about that sort of size. And then you suddenly, at the very edges, have these like 1 to 2 kilometre sized mountains just coming out of nowhere. They've done some modelling on it, and what they suspect is happening there is that actually along the whole edge of that ring is lots of very small moons. So we're talking probably about a couple of 100 kilometres, 100 metres or so, not kilometre. And they're not big enough for us to actually see with the images, but they're big enough to actually vertically scatter ring material. So as individual ring particles get close to these bigger particles, you can actually throw them vertically, and it creates these kind of mountain structures that we can see. Although they only seem to be located in that part of the ring, they don't seem to be all the way throughout. So something's herding them in that location. Now, back to the gaps that the moons actually form themselves. Again, I'm going to use the analogy for planet formation, because as planets form, they actually then start to create a gap in the disk. And if they get to a certain size, they will create a gap. And it's the same with moons. Once they're a certain size, a certain mass, they'll clear out any material nearby, and they have this kind of gap all the way around. They've got to be a certain size, and the actual width of that is proportional to the size of the moon. What it does, it basically it gravitationally pulls ring material towards it, which will then send it on a different orbit, so it moves it either further out or closer in. And this is actually not Saturn's rings. This is a disk around a star that we found. So these are some images taken of the star, and you can see there's a disk around it. And it looks like it's actually got a gap. It's got a gap around it. So we haven't actually found a planet, but there's a gap. And by looking at what's the effect on that disk, we can work out there's a planet there, and we can work out kind of the size of the planet. An artist's impression, they're always good. Because the scientific images don't always explain what's happening there. So that's an idea of what's actually the system is. And you can see that actually there is ring material, or disk material, being pulled from one side in, and that's actually how planets migrate. They actually they can move inwards, and what they do is they pull the disk material over, and they displace it further out. And that's how they can migrate in that. And I'll show you more towards the end, but we actually saw a moon forming in Saturn's rings, and it was migrating outwards. So again, it's useful for planet formation theories. If the actual moon is not big enough, it creates a different structure. You get these propellers, and there's hundreds of thousands of these propellers in the rings that we look at. And they look just like a propeller. They're orientated in the way they're orbiting. So as they're orbiting around, you get these propellers in front and behind. Again, because it's orbiting faster and slower on either side, it's why it looks slightly asymmetrical, a bit like a propeller. But they're typically about couple hundred meters in size. They're not big enough to create a complete gap, but they are big enough to actually scatter particles nearby. And it creates this fairly subtle structure like that. Again, we did some modelling, and it shows you that this is pretty much what's happening. And by looking at the structures in our models, again, you can predict, or you can work out the exact mass and the size of the structure that's causing that. So it's a very useful thing to have. I haven't got any audio, but if you get a chance, search for radio signals of Saturn if you haven't already heard it before. It basically sounds like the soundtrack of a B movie, a science fiction B movie. It's really eerie, but the aurora that you get around Saturn, it creates this really strange radio signal, and that's it kind of in graph form. But I would recommend you go and find the actual audio and listen to it, because it's quite an interesting sound. So Saturn's a much larger planet than Earth. It has a much larger magnetic field, so it has actually much larger aurora. It has, that's an actual image of one there, and they're quite active, and we can actually hear them from Earth. So if you get a radio telescope and look at Saturn, you can hear them from here. But the one thing that Cassini actually got to hear was actually lightning strikes. So lightning strikes will create a fairly significant radio output, and they actually visually observed one there. So that was that storm we saw earlier, and where the arrow is, there is a blue lightning strike. I don't know if you can see it well there. And on the right-hand side, it's the same location where there's no lightning, just to show there is lightning happening. And then the radio signal from that we actually managed to pick up. And you get a lot of lightning happening on Saturn, and they've managed to image it quite a lot. And, you know, it gets quite interesting when you start to see these things happening on other planets. So it's not just Earth that has lightning and all these other things. Saturn's got exactly the same things. And I'm sure we're going to see exactly the same sort of things happening with Jupiter. So now that Juno is with Jupiter, we should start to see a lot more things that Cassini's been doing, but with Jupiter. I should have a video. Yeah, so that is a video showing the actual the charged particles from the solar wind interacting and basically creating the aurora. In case you're wondering, all of the bright dots that are moving upwards, they're basically background stars. So the background stars are fairly bright in comparison to what they're actually looking at with the spacecraft, so you see them quite easily. And the aurora's, you know, the faint bit there. So the aurora are quite important, really, and the magnetic fields that create them, they're very important for keeping the atmosphere. So things like Mars has got a very weak magnetic field, and it's got a very weak atmosphere. It used to have a lot stronger one, and it's the one thing that protects us, and it protects a lot of the actual other planets. A lot of the moons are actually within the magnetic field of Saturn. I don't know whether that's a good or a bad thing, because it means that actually sometimes a lot of these charged particles are funneled to the actual moons themselves. Now we know that there was a comet that actually impacted Saturn and the rings in 1983. We didn't see it, but we know it happened. And the reason why we know it happened is something happened to Jupiter that we did get to see. So in the 1990s, there was Comet Shoemaker, I think, and it got to Jupiter and it was pulled apart into about 9 pieces, and then it impacted Jupiter. That was quite an exciting time. But Jupiter has rings as well. And by looking at what it did to the rings, and then working back and thinking, well, we know that it basically bent the rings and it created these vertical ripples. Saturn actually has the same. So Cassini found that in the inner parts of the ring, you have these vertical ripples. On the left-hand side is actually a model which shows how they evolve. So over time, they kind of get tighter, they get more wound together. So they can actually work back from that to find out when these sort of things happen. So you need to observe it first. So this was actually the Jupiter one. So that was the comet there that was pulled apart. So when I mentioned about the Roche limit and anything that gets within it is pulled apart, that's what happens basically. It gets too close to a very large planet, it's going to get pulled apart, and then that then impacted Jupiter. But because it hit it kind of off axis, the rings around Jupiter were then gravitationally bent, and it created these vertical ripples. And you can see basically the actual images and the models, and then once you can match your model to the actual observation, you can work out mass. So this then brings us to that I spent the most part of the last few years doing. This was my area, which was the F ring, and it's about it's the most dynamic place in the solar system. So it's somewhere that is constantly under attack by the nearby moons. There's new moons and moonlets and clumps forming, and it happens kind of on an hourly sort of basis. So it's very dynamic. It's very thin, and it's just out on the outside of the main rings, and it has these 2 moons that shepherd it. They kind of keep it that narrow, but they also actually attack it at the same time. So they're basically very large potatoes. The reason why they're kind of that shape is because of their size. once you get to a certain sort of size, they actually start to become a bit more spherical. So the gravity itself actually shapes it a bit more and then become a bit more spherical, which is why you don't get a potato planet. But these moons are only about, see, I think Prometheus and Pandora are about 50 to 100 kilometers. So 50 width, 100 kilometer long. So they're fairly small moon, but they're moving towards the ring and back out again, and you can see on the bottom right there that there's Prometheus has basically disturbed the ring and created these kind of structures. That's quite tame for what it normally does. So another image of the F ring, and Prometheus would be down on the bottom left here. So it's moved around, and it creates what we call streamer channels. So when it first goes near the ring, it then gravitationally pulls out these strings of material, which is the streamer. And then about half an orbit later, all the ring material goes back again, and it creates these channels. And what they found was actually that at the edge of these channels, where the red circles are, they were high density. They also found that these, I haven't got a picture, but there was these fan structures in those exact locations, and that tells you that there's another moon there that's actually creating these fans. Which is quite interesting, because if there's moons located there, and Prometheus has actually created those features, does that then mean that Prometheus, the moon, has created them? Well, I'll show you some models later that might show that, but this is to show how dynamic it is. So these are on the top, basically, images of the full F ring, and each one's different. So at different orbital phases, there's different things happening, and it's constantly being under attack. And I'll go back again to the Roche limit I mentioned about things being too close to the planet and being tidally pulled apart. The F ring pretty much sits, within a few thousand kilometers of that limit, and it means that it's competing with the strong tidal forces of Saturn, and it's also got these moons stirring it up. So you can get things, clumps forming, new moons forming, but they can quite quickly be destroyed as well. And the one on the left-hand side is of the F ring. So some of these new moons that are formed actually then go crashing through the ring, and you get what you call jets. So on the bottom is some models, and on the top is the image by Cassini. And you can work out the trajectories of these moons. So you can't always see the moon because they're quite small, but you can see the signature at least behind, and you can see those jets. And by creating a model to replicate that, you can actually work out more about the moon that might have caused them. And again, you've got the propeller structures there. It's just a very useful way of finding more out. And we have to use the physics we already know to try and replicate them. And if we can replicate them, then we're fairly happy with the physics. And on this one here, again, it's the F ring, and you can see that the density in the model represents where the density in the Cassini image, or we assume that a surface brightness represents a high density. So we know that actually the density does increase. It's just a useful tool to have, actually. Another useful thing about doing modelling is that actually it's not like a real system where you're just taking an image and you can see where the particle positions are. You can work anything out. So you can work out how fast the particle's going. You can do a whole load more parameters, basically. It's very useful. So by doing this and looking at those high-density regions, stuff like that, you can find that actually there's more interesting things happening than just the increase in density. You find that actually along the channel edges, you can actually get some quite high velocities. Another thing about forming clumps and stuff like that is you don't want fast speeds. So if you want two particles to come together and gravitationally stay together and then grow, you don't want them actually to impact each other at high speed, because they're not going to, things are just not going to grow under their own gravity. So by looking at these kind of velocity dispersions is where you can find more out about that sort of thing. I mentioned the fans. The bottom right hand there is actually along the channel edges. It's quite small, but where the F's are is actually where those fans are, and where the smaller moons are actually located. And again, this is the idea was to try and do the modelling and see what happens there. And I think it was a couple of years ago now, this was a new moon that just appeared. So at the very edge of the A ring, which is the edge of the main rings, you saw this on the edge. So and I still don't know whether they actually know it's an actual moon or whether it's actually just a clump of material. I don't think they've actually decided. But it wasn't there to start with, and it's most likely migrated out from the main parts of the ring and come further out. And if it continued to do so, it's possible it could have actually turned into a new moon and then continued to migrate further out, and joined a lot of the other moons, basically. So these are very useful things to find out. And then it brings us basically to a few things of the final science, really. So it did some very dangerous manoeuvres at the end. It got very close to the actual rings, and as a result, you got to see some, really detailed pictures. And if these are very close up, and you can see that actually, although we know the rings are not smooth, you look even closer, and they appear quite grainy as well. So even on a much smaller scale, you've got a lot more of a grainy structure there. Again, the bright objects at the top are basically just background stars. A very close-up detailed image of a propeller there. A very nice image of the actual atmosphere or the cloud structure of Saturn. It almost doesn't look real. It could almost be a painting, that, but you got quite close and got some nice images of the clouds. And another thing, I mentioned at the beginning that the actual rings themselves are made of water ice, so they should pretty much be white, but they're not. The top image on the right is the actual the true colour, and on the bottom it's showing you that actually, so the reddish telling you that it's redder than it should be, and the blue is slightly bluer. This was done fairly recently, and it's just, why would that be the case? It might be there's certain bits in there that actually is changing the colour of it, but it's interesting nonetheless. But that basically brings us to the end. And I have got, if anyone wants to have a look later, this was some images, drawings taken in 1848. And that was basically what we knew about Saturn then. This is kind of what we know now. And it'd be interesting to know what we're going to know in the future, basically. So if anyone wants to have a look at this before we go, they're welcome to. It's quite interesting, actually, to know what we thought about Saturn 150 years ago. Yeah, that brings me to the end. So if anyone has any questions, you're welcome to ask. Yes. Rings are typically quite short-lived in astrophysical terms. So the fact that Saturn has quite significant rings is a bit of a puzzle, really, because all the other planets have got very thin rings now. What happens is they basically, if I go back to so this image here, I can't say for sure this is what's happening here, but what they know is that material that expands beyond the Roche limit clumps into moon, and then it kind of migrates outwards. It forms part of the moon structures, and then the rings kind of come back again, and they expand. It's like they refer to it as like a viscous spreading, so you imagine it like a fluid. And then that happens over a long period of time, and basically a lot of it then just turns into moons. The fact that Saturn still has rings, when it probably shouldn't, means that something's happened. So we think there might have been a Titan-sized moon that got too close, that was just completely pulled apart, created the ring, and then it all starts over again. But the actual rings themselves, as they are wider there, still a bit unsure. Most of them will be, well, they're all rotating. I couldn't tell you which ones are tidally locked and which ones aren't. So some moons, for example our moon, is tidally locked, which basically means that it rotates on its axis exactly the same time it takes to go around the Earth. I don't think any of Saturn's moons probably are. The reason I'm going to say that is because they have a lot of tidal energy in them, like for example Enceladus. So that, it most likely isn't tidally locked. But they'll all be rotating in some form or another. If it's a captured moon, it can rotate in the opposite direction. So you get things like retrograde moons, which Saturn and Jupiter have, where it's an asteroid that's come too close, and it's orbiting in the opposite direction to everything else, which is weird. A bit problematic for other moons, I would imagine, but... Yes, I think, as far as I'm aware. They were doing analysis of the plumes before Cassini ended its mission, and from what I can remember, I think they did find evidence of hydrocarbons. It might be worth checking on that, but I do seem to remember reading something a while back about it. That's why, in fact, I think it was earlier this year that NASA actually did a press release about possible life on Earth, so I think they did find more evidence along those lines that would suggest that. So, I think on my first slide, I think Saturn's about 58,000 kilometers, or it's about 60,000 kilometers in radius, and the Earth is, about 6? So, radius-wise, it's about 10 times. You can work the volume out-wise. In fact, on my very, very first slide, I had the exact size comparison. So, at the top there, that's the Earth, as it would be next to Saturn, and size-wise, to get you a feel for it. So it's quite a lot bigger. I'm not so sure on that one. One thing that we do know about our own solar system is it's very unique. So as we go out and find other planets around other stars, they're not configured the way ours are. So all of their gas giants are actually very close into their stars. Ours are further out, and the way that ours formed is they don't fully understand yet, but all of the planets when they formed were interacting with one another, that's prevented them from kind of migrating inwards. That's as far as I can tell you with regards to the formation of Saturn. I don't know much more, unfortunately. Probably indirectly. If we're going to Saturn and we're looking at the rings, it helps us understand some planet formation ideas. So if you understand those sorts of things, it can help you understand how the Earth came about. They're all tied in together. And it comes back down to how the Moon and the Earth formed as well. So they think that there was a collision between the Earth and a smaller planet, and that then created a debris disk around it, which then formed into a moon. So the Earth would have had some kind of ring structure similar, well, I won't say similar, but it would have had a ring structure which then formed into one large moon. So if we can understand how moons and stuff like that are forming around Saturn, because it's there and we can see it right now, it's a bit indirect, but we can still help us understand a little bit more about how these things happen. I haven't seen anything, to be honest. In fact, actually, I don't seem to have read anything about or come across anything with regards to the tectonic activity or anything like that on Titan. I have about the other planets, so the other moons like Enceladus, the actual the crust is moving around a lot, it's floating on the liquid ocean, but Titan I'm not sure about, but you're right, it does have mountains, they don't just appear. They have to get there somehow. With the smaller moons, a lot of those structures can come with the way they form, so they're a bit like an asteroid, so as they grow, they're not quite big enough to be spherical, so you're going to get uneven accumulation on it. But Titan's big enough that it has to have a different process to create them mountains, and I'm not sure of that. If it was my choice, I would probably go for Europa or Enceladus, because we know we've got water there right now, and it's at the right temperature, and there's a few other things. Whereas Mars, it could have had life. In fact, to be honest, one thing that got me interested in doing a lot of this stuff was I read a book when I was a kid about when they thought they'd found life on Mars. I still don't know whether actually they have decided if that was life or not. Some fossilised potential bacteria, but it got me interested in that whole thing anyway. But I would send it to one of the moons instead. Something else I'm working on at the moment is looking at exomoons. So there's a lot more moons than there are planets in our solar system, and that goes for other systems as well. And I mentioned that a lot of these gas giants are very close to the stars. They're not habitable, but they are close enough that if you had an Earth-mass moon around them, they could have life. So maybe the best place to look for life outside of the solar system is actually on exomoons, and not on the planets, because there's going to be a lot more of them. We just need to find them. They're quite small compared to the large planets we've found, so they're difficult to find, but they might be our best hope outside the solar system. Yes. There's a lot of interesting things happening. So I can't remember the exact names now, but there's a few moons around Saturn that they switch orbits with one another. They just, I'm going there, this one's going there. They're called like Trojan moons. So they're very, very weird. So they exist in the same orbit, but they do, with respect to one another, they do horseshoe orbits. So they do very strange orbits, but basically means they can switch between. It's actually the same as what you have with Jupiter. So Jupiter has like the Trojan asteroids. So 60 degrees in front and behind you have these large asteroid groups, and it's because Jupiter effectively herds them there. And you have the same thing with Saturn's moons. You have like smaller moons, the larger moons. They're in these very strange locations. There's a lot of resonances there, so that certain moons orbit, say, for example, 2 or 3 times for one orbit of one other moon, and it means that they're kind of locked to one another. And there's a lot of that occurring there. So they're all interacting, and a lot of that very fine ring structure you see, that's because of all those rings, all of those moons affecting the ring. So it's a very dynamic place, and it's why it's of interest for studying a lot of other things than just the actual rings themselves. Did I not say? That's terrible. So the ones you saw in the gaps, they're typically about 5 to 8 kilometre sort of size. The ones that create the propellers are around about 100 metre size. Any larger than that, well, they actually scale a bit, so the smaller moons are kind of closer in, and as you go further out, they're a bit larger. There's some model that shows how they form. So Prometheus and Pandora are on the edge of the main ring. They're about 50 to 100 kilometres, and the ones a bit closer in the gaps, about 5 to 8 kilometres. Sorry, what was that? It did. So it found there's a lot of hydrocarbons on Titan. But as far any more details than that, I'm not sure on. I was more, my work aimed more at the rings themselves than actually of the actual Titan mission. But I know that there's a lot of different types of hydrocarbons there, maybe methane and a few other things, but that's as far as I know, unfortunately. It will be fairly comparable. They're already kind of in big trouble, the rings, because of this field. Basically, yes, as you saw with the aurora, you get the solar wind, and a lot of the charged particles are effectively, they follow these field lines, and the problem is that these field lines go through the ring, they actually go through the moon. So Enceladus, I didn't show you a picture of it, but there's actually a connection between Enceladus and Saturn itself. It almost creates this electric field, which almost, you can see it coming out the bottom. But it does mean that, for example, Cassini has had some quite significant, it goes through some significant electrical charges where it was orbiting, getting quite close because of these fields and stuff. If it switched, I'm not entirely sure. The same as if it switches here, I'd imagine. It's not catastrophic. We carry on. But I think ours switches every few 100,000 years, something like that. And we're okay. Ooh. So there was, when Cassini first got there, I think when Voyager first went past, they saw these kind of spoke structures. And they're very small particles, and they come out radially. So if you, as you saw on the images of the rings, you saw these lines going across, which are basically in the plane that they're orbiting. But these spokes actually went perpendicular, the opposite direction to them. And they were actually manipulated by the magnetic field of Saturn. And it was these smaller charged particles that kind of lined up with them. The idea was that they could look at these structures and find out internal structure of Saturn by looking at the magnetic field. But I've not heard anything more recently about that. That was the beginning part of the actual mission, I think, was looking at these sort of structures. Around Saturn? They'd probably be gone. Probably a few more rings. They'd be gone. You'd say 1 billion years. Okay. Because that sort of time frame, we're all in big trouble anyway. Because the actual the sun's gonna, when it gets to the latter part of its life, it's going to expand into a red giant. So you're okay if you're on Saturn. In fact, if we find life on one of the moons, we should probably go live there, because at that point the sun's going to expand quite a lot. And I think, it's going to come a lot further into the solar system. It won't be habitable here. So people are always going to ask, why are we doing this? Why are we looking for other planets around other stars? Well, the extreme long-term view is actually we do need another planet to live on. That's if we're still here in 1 billion years. But yeah, in 1 billion years, the actual rings themselves will probably have formed into moons and stuff and dissipated. I think because of what we've found, I'll be surprised if there isn't another one that goes out there. Because when we sent it out there, we've discovered things that we didn't even think were going to be there. So we didn't plan for those things. So now we know they're there. Maybe we can build a spacecraft that's got more equipment on, can look at better things. And I've already, there are already people proposing additional missions to Saturn for scientists. So I think it will happen. But the problem is these things take a long time to plan, they take a long time to build, and then send out there. So, Cassini was probably thought about in the 90s or 80s. So it was done a long time ago. There's a very long-term sort of mission. They take a long time to plan and do. But I would like to see another one because there's a lot of unanswered questions there. Well, I suppose for us, if we kind of make our planet more tilted over, we're going to get more severe seasons. So that will then affect all your weather, your climate. So that's what's going to happen. Well, that is what changes. So the rotation, if you change the rotation axis, it's going to be, you're just going to get more severe seasons and stuff like that. With something like a moon that far out in the solar system, it's not going to get that much sunlight hitting it anyway. So, I don't know, it might be more of the actual tides it gets from the planet itself that might be more destructive. But that's probably what's going to happen.